Welcome back to Codex. Our speaker today is Ilya Krishtal from Northern Illinois University. Professor Krishtal is an expert in applied and abstract harmonic analysis. He'll tell us about some Kadec-type theorems. Take it away, Ilya.
Thank you very much for the introduction and the invitation. It's a fun and pleasure to be here and see a lot of friends online. So I hope you will be here still in an hour. Anyway, so the talk is about Kadec-type theorems. And this is something that I wasn't expecting to be doing at the beginning of the year, but at some point, my PhD student, Brendan Miller, listened to a talk by Ilya Krishtal, and Ole posed a conjecture. So Brendan came to me and explained that conjecture to me, and we started thinking. We didn't solve the conjecture, but one of the things we decided to look into were Kadec's theorems, and we ended up with a preprint and this talk. So I'll hope you enjoy it. All right, so this is the short outline of what I will present. I will give you a little bit of a history of the Paley-Wiener constant, which led to Kadec's theorem. So I'll go through the theorem. In fact, I'll go through most of its proof and discuss a few generalizations of that. And then we'll go into a different direction for generalizations, because the exponential frames that Kadec's theorem talks about is an example of dynamical frames. And Ole's question was about dynamical frames. So that is what connected the two in our minds. And we started thinking, well, can we do Kadec's type theorem for dynamical frames? And that's what we did. So I'll give you that generalization, and I'll show you that the proof is essentially the same. So there is very little that needs to be done to extend Kadec's theorem to a much more general setting beyond the system of exponentials. And so much beyond that, it doesn't have to be even a Hilbert space result. The techniques do work in a Banach space setting. So if we still have time in the end, we'll see the extension for the case of atomic decompositions in Banach spaces. All right, so that's the story for today. Let's start. We all know what frames and Riesz bases are, but let me confuse you and give you some notation and a slightly different definition, well, a little unusual. So to fix the notation, my capital Phi is a system of vectors in a Hilbert space. Given that system, I get an analysis operator associated with it in the usual way. I take the inner products of my vector x against that system. Its adjoint is called the synthesis operator. And then once you take the product of the two, you get the frame operator. And then if the frame operator is positive definite and invertible, then that system is a frame. And if the synthesis operator is bounded below, then the frame is actually a Riesz spaces. All right, and of course, we're used to looking at inequalities like this in the definition, and they are, of course, equivalent. Right, so here I define the frame bounds. This is the frame case. This is the Riesz basis case. All right, it's the usual definitions. It's written this way just to fix the notation for the analysis operator, synthesis operator, and frame operator, and the frame bounds. Okay, so let's move on. What is the Paley-Wiener problem? Well, they studied many, many things. One of the things they did study was in 1934. They looked at when a system of exponentials forms a Riesz basis for H. All right, so we all know, of course, that if you take the standard basis, it's an orthonormal basis on L2 negative pi pi. And then what happens if you perturb the integers? The question that Paley and Wiener asked was, by how much can you perturb the integers so that the system remains a Riesz basis? Right, so the Paley-Wiener constant is the largest number, capital D, such that if the sup of these perturbations is less than that d, we still have a Riesz basis. All right, so the natural question is, what is the value of d, which after that paper started to be known as the Paley-Wiener constant. All right, so let's see what happened. All right, that's their question. What is the exact value of capital D? Well, already in their own paper, they showed that D is at least 1 over pi squared. That's, I remind you, is 1934. And 2 years later, Levinson showed that it cannot be bigger than 1/4. He gave an example that shows that you cannot do better than 1/4. 1/4 doesn't work. In a sense that if delta is 1/4, you have examples of systems like this, which are not Riesz bases. So 1/4 is best it can be. And then after another 6 years, Duffin and Ekus improved 1 over pi squared to 1 over pi log 2, which is approximately 0.22. And that's where it stood for over 20 years until Golovin came around and turned 0.22 into 0.24. So now we just have 1/100th of a gap. And 1 year later, Kadec came around and showed that there is no gap, it actually is 1/4. All right, and this is the theorem that most people in the field know. I knew it for quite a while, and I never had a reason to actually look into its proof. So I thought it's an ingenious and complicated result, but I had other things to do, so I never looked into its proof until Brendan came and talked to me about Ole Christensen's conjecture. And then I had a reason to look into the proof, and I was surprised because the entire paper is 2 pages. And the proof is rather simple. It's ingenious, but it's not complicated. All right, so let's have a small detour in, well, it's not a detour actually. Let's just look at the proof. And the proof is based on the lemma which Paley and Wiener proved themselves back in 34. So they started with a system which is the standard basis, easy. And then the lemma says that if the system of exponentials is close enough, then it is a Riesz basis. Well, what does it mean, close enough? Well, you're looking at the difference of the synthesis operators. And if the norm of the difference is less than 1, then the new system of exponentials is a Riesz basis. All right, so to prove Kadec's theorem, one needs to look at the estimating this norm. All right. Okay, well, let's do that. We plug things in, just explicitly writes what those synthesis operators are, and we get this norm. So it all comes down to playing with this difference. And this is where the ingenuity of Kadec came about. He, for some reason, decided to take this function and decompose it against the orthogonal basis of this form. All right, so you're taking the standard cosines, but you're shifting the signs by 1. All right, so this is a generalized Fourier series where the signs are a little bit different. And the beauty of this expansion, if you notice, these series in nu are absolutely convergent because of the squares there. All right, so this is an absolutely convergent expansion for this function. And then you go ahead and directly estimate this norm by breaking it into 3 pieces according to this expansion. All right, so the first piece that corresponds to the constant term is estimated here. This is the estimate for the second piece. And the beauty is that you can replace this delta k with a soup of delta k's that is delta. Right? And you can do that in the third case as well. Even though cosine is a decreasing function, once you look at the entire series, that's still increasing, and you can again replace delta k with delta. Right? So you have these three estimates, and then you combine them together because this is what you care for. And these miraculously have a closed form expansion. So when you add these things together, you simply get this. And this is going to be less than 1 as long as delta is less than 1/4, and that's the entire proof. All right, so notice that we started with the function here, and we got the estimate, which is very close to what we started with. Okay? So that is Kaditz's proof, and I will show you a little later that essentially the same idea works in a much more general setting. But first, let's look at generalizations of the theorem that go in another direction. Right? And ideally, Brendan and I would want to get these generalizations for our setting, but for them, you need much more sophisticated techniques for the proof. These aren't just ingenious, they're also complicated. And for now, we weren't able to go to our setting yet. So what did Katznelson do a few years after Kadec? Well, basically, the way to view this generalization, you could think of it this way. So originally, the basis was on a grid, and you could go up to a distance of 1/4. Right? In Katznelson's case, the original basis doesn't have to be on a grid. So if this is the original basis, you could have different distances between the points. And then what Katznelson says is that as long as you're perturbing each of them by less than 1/4 of the distance to the nearest one, you're fine. This is morally what this result says. Right? So this is a generalization by moving the original spectrum from the grid to an irregular set. And then the state-of-the-art result in this direction is Avdonin's theorem, which is 10 years after Kadec, where he says that what you care about is the average displacement being less than 1/4. Right? So you're averaging the displacement. In both of these cases, however, you need to make sure that your points don't collide. Right? So ideally, we'd want to get an extension of this result for our setting, but we're very far from that. So in case someone is interested to join us, we'd be very happy to listen to your ideas. Right? But before we go to what we can do, let me show you another generalization which goes from Riesz bases to frames. So back in '97, Radu, he was probably a student back then, showed that the original system of exponentials need not be a Riesz basis, it can be a frame. And then if the original frame has bounds A and B, there is the delta bound, which becomes 1/4 if the frame is parsable, so that if the perturbation is bounded by delta, the new system is still a frame and you have control of the bounds. Right? So the generalization that Brandon and I get, in fact, works with this theorem rather than the original Kadec, but in a way, the proof is still the same. It's just the starting point is a little bit different. It's a slightly more general version of Paley-Wiener lemma, which is due to Ole in Hilbert space and Ole and Riesz in case of Banach spaces. All right, so what was Ole's result back in 95? Well, if you have the synthesis operator of a frame with these bounds, and a new synthesis operator for another system, as long as you have this bound, right? Remember, in Paley-Wiener, the bound was just this part. Here, there is a more general way of bounding it. Well, then as long as you have this bound on lambda and mu, the new system remains a frame with these frame bounds. So what Radu did, he used this theorem and Kadec's argument to arrive at his version of Kadec's theorem for frames. And this is what we will do in a more general setting, which applies for more general dynamical frames. All right. So what are dynamical frames? Well, a frame is called dynamical if it's an orbit of a fixed vector under a bounded linear operator. Right, so I fix a vector in a Hilbert space H, I fix a bounded linear operator, and I look at its orbit. And if it's a frame, then I call this frame dynamic. And Ole's question is actually much more precise than what I have here, but in principle, what he's after is the description of the subsystems of a dynamical frame, which are themselves frames sequences, or perhaps frame for the whole thing. So Ole is specifically interested in what's called Katznelson frames, and there are subsystems which remain frames for the whole space, not just frame sequences. Right? And when Brendan came to me and talked to me about Ole's question, we thought, well, exponential frames are dynamical because we keep multiplying, we keep applying modulation to the constant function, right? That's what an exponential frame is. You take a constant one and apply modulations, you get the standard basis. So can you get a Kadec-type theorem for more general dynamical frames? And then eventually, can you use that more general theorem to say something about all this question? Right, so with the second part, we still don't know. We're still working on it. But with the first part, the answer is yes, and I have something to talk about. All right, so I will give you that theorem. But before we go there, let's actually get the setup. Okay, so I fix a bounded operator A with a spectrum being real and a subset of negative pi pi. You can take any interval you want, but because you can always move things. But for simplicity and keep in line with Kadec's proof, we'll just take the interval negative pi pi. And then we'll look at the group representation where we simply look at the exponential map, e to the ita. All right, so this way we get a uniformly continuous representation of the group by operators in B of x. And notice I'm using a Banach space because here I don't care if it's Banach or Hilbert. Right? This works either way. And then in a Hilbert space, the question is, well, I'm looking at suborbits of the orbit. I take countable suborbit and I ask a question, well, when is this a frame or a respaces for the entire set X? All right, and what is the analog of Kadec's theorem in this setting? That is our question. Okay. All right. Here's the answer. And you notice I have exactly the same bound as Radu had in his theorem. So I fix a vector x and h in a Hilbert space H. I fix the spectrum gamma n. I look at a suborbit, which I know is a frame for H with known bounds. And then I look at a perturbed system such that the soup of perturbations enjoy this bound. And then the new system also forms a frame for H with bounds as in Radu's theorem. Moreover, if you start with a Riesz basis, the perturbed system will also be a Riesz basis. Right? So that's the result. And now let's look at some ideas in the proof and a little bit of the sketch of the proof. So the key thing is the functional calculus that you can make for the representation. Right? So if you start with an L1 function, then this integral defines an L1 module structure on X. Right? This is a continuous function, so the integral makes sense. And because function is also L1, you can integrate. And it's a Banach module because the norm of fx is going to be bounded by the one norm of f times the norm of x in our space. Right? But because the spectrum is in minus pi pi, your function f doesn't necessarily have to be in L1. What you can do is you can, on the Fourier side, you can multiply your function f, or I call it h in this case, by some Fourier transform of an L1 function, which is 1 in a neighborhood of negative pi pi and has compact support. Right? So I effectively convolve f with phi, or on the Fourier side, I do the multiplication. So I extend my module structure from L1 to this FL1 lock algebra. And then, once I have that, I can repeat Kaditz's or Radu's proof, replacing the function that was 1 minus the exponential with this guy where h is, again, 1 minus the exponential. Right, so let's see a little bit how this works. Right, and what I'll need is a result that Baskakov and I published back in 2014. It was a part of a long paper, and there was kind of a sideways result there, which wasn't really needed, but we thought it was cute and maybe someday it would be useful. We didn't think too much about it, and suddenly it became the key result that we needed for this paper, which is 10 years later. So this is to show that sometimes little theorems that you don't think much about come around very handily much later. All right, so what is this? Well, if you look at the function h, which has this representation in terms of the absolutely convergent series, right? My C is an L1 sequence here. Then the structure, this module structure that I defined here for this function h is nothing but this. Okay. And now I'm back to Kaditz's proof. Right, so I again define my delta n as a difference, right? That's my perturbation. And my hn is going to be that function that we worked with back in Kaditz's proof. So we're going to use the same orthogonal expansion for this function. Right? And according to Christensen's perturbation result, what we need to estimate is this difference. Right? But once you use the theorem by Baskakov and I, notice that this is of this form. Right? So that means that this becomes that. Right? So we now need to estimate these diamond products where h is the function that Kadec had in his proof. Right? And all we need to do is the same thing that Kadec did. Right? We expand each of these functions the same way. Right? So these are exactly the same expansions that Kadec had. And then the norm that we need to estimate breaks into three pieces, just like in the Kadec's case. And now working through, right, so this inequality is not exactly immediate. You have to make sure that all the definitions make sense. But in the end, that's rather routine. You get back the expansions that Kadec had in his proof. So it's exactly the same roadmap, albeit these constants pop out just like they do in Radu's proof. Right, and you're back with the same estimate that Kadec had. Right, so once you're in the right framework, you're doing the same type of orthogonal expansions, right? So there's nothing really about exponentials here anymore. Okay, and then once delta is small enough, this whole thing becomes less than 1. Christensen's theorem applies, perturbation theorem applies, and the result is the frame, and that concludes our proof. Right? And you get the bounds just like you get them in Radu's theorem. So once you have the right framework, the proof really doesn't have anything new in it except the use of this guy. We use it twice to go from here to there, and then back when you do the estimations from here to here. Right? But that's the only new thing that goes into the proof. The rest is really just Kadec's argument in the form of Radu. Okay. Well, let's look at a few consequences of this. So first of all, if you look here and follow through this argument that's not on the screen, you would see that these guys, right, this is our original frame. This really doesn't even have to be in orbit. So as long as these are equal norm vectors, right, so this could be some phi n. So you start with original frame, equal norm frame, which doesn't have to be a suborbit. As long as the perturbation is via these representations, the result will still hold. All right, so that's the first observation. The second observation is a little curious. Well, you start with a Riesz basis, if you start with a Riesz basis and perturb it, as soon as the points collide, you no longer have a Riesz basis. So the bound has to prevent collision of the two perturbing points. And that allows you to establish control over the ratio of the lower and upper frame bounds. So you can control the condition number using the gap between the original points. So in other words, what it says, if you have a gap that is very small, you cannot have a good ratio. So making the gap smaller necessitates the decrease in the ratio. Right? You get it kind of for free. And another interesting thing, the same method gives you an improvement if you want to estimate this operator norm. Right? This type of norm is very useful in many other results that Baskakov and I proved in that paper that I cited, the 2014 paper. And the estimate there was like 4 times bigger than what you get from using these techniques. So you get a much better number. All right. And I guess I went through the talk a lot quicker than I thought. But we do still have a small piece about atomic decompositions. So this is the definition of atomic decomposition that comes from the paper of Ole and Ole Christensen and Chris Heil, where they extended Ole's result to Banach spaces. So you look at a complex Banach space, and this is its Banach dual. And then a pair of sequences forms an atomic decomposition if you have these three properties. So you have a frame-like property, but you have to have more, right? The frame-like property in a Banach space doesn't necessarily imply the decomposition like so you have to require it in the definition, right? And this is an atomic decomposition with respect to LP for some P between 1 and infinity, right? So strictly less than infinity. And if you carefully look through the proof of our result, then you notice that there's nothing there about being Hilbert, right? So you use the perturbation result that is due to Ole and Chris, run through the same program, right, without any changes really, and you get this monstrosity. All right, so what happens is you have to require a little bit more, right? You have to require that the synthesis operator is actually bounded. Right? And in this case, I went for a more general interval, so there's a gamma here. Right? In case of gamma equal pi, you get exactly the same number there, but notice there is a little bit of a difference, which requires the use of this norm of the synthesis operator because, well, we're using the result of Ole and Chris, and that's what we have to have. All right. And again, if you start with a basis, the perturbed system will also be a basis. Okay. So this is what we have. And as I said, would love to do something more in terms of Ole's question or in terms of Avdonin's theorem. We're not there yet, but on the other hand, we only started working at the end of spring. So this is still very much an open thing. And I think I did go through it much quicker than I thought I would. So this is the preprint that's available for you in archive. I didn't explicitly cite the papers, but they are in the references, so you can get it from there. And I think we have quite a lot of time for questions.
Great. Let's see, I'm going to hit this button here to show my appreciation for that talk. And I encourage you to do the same.